Okay, so so the Lorentz transform velocity addition rule along the x direction, this is for velocities along the x direction, um, basically converges to the Galilean transformation when v over c, that is beta, is much, much smaller than 1. So at non-relativistic speeds, we recover the Galilean transformation, which is satisfying because we know that the Galilean transformation works well in our everyday experience when, with low velocities. Now, we may be tempted to think that the velocities of an object measured along y or z, that is, if this observer here, if this person threw a ball up instead of to the right, threw the ball along the y direction instead of along the x direction, we may be tempted to think that that the velocity that the person in the unprimed frame would measure would be the same as the person in the primed frame. But remember that we have other factors like time dilation that are that will keep that from being true, actually. Okay, so even though the coordinate values along the y axis as measured in the primed and the unprimed frame are the same, the velocities along the y and the z direction, that is the directions which are perpendicular to the relative direction, to the direction of relative motion here. Remember, v is along the x direction. So velocities, the velocity components which are perpendicular to the relative motion are not going to be identical, okay, even though the coordinates that they measure are. Okay, so how do we, so basically we go through the same analysis to get the velocity transformations along the y and the z directions. We go through the same analysis, but now instead of plugging in for x prime, we plug in for y prime, etc. So so again, this is what we wrote on the previous view graph. This is the velocity transformation for along the x direction. Okay, so for the y direction, if we use the fact that, again, the coordinate values are the same as measured in the primed and unprimed frame, dy is equal to dy prime, and then we plug in for the Lorentz transform equation for the time coordinate, okay, and we just again we divide the two, so dy divided by dt, okay, then we get this expression. Now again, if we divide the top and bottom by dt prime, again we're dividing by 1, so it's we haven't really done anything. Then we get that uy is equal to uy prime divided by gamma times 1 plus v times ux prime divided by c squared. Okay, this is a prime. So we see that the measured y value, the velocity value, actually involves the x component of the velocity of the object in the primed frame. Okay, so that's interesting. The other thing is that I should probably rewrite this to be more general. Sorry. Okay, so I've rewritten this expression for the x direction more general, since now we're basically considering we're considering the case when the velocity of the ball in the primed frame can be in any direction. So the person can throw it in any direction, and so we have to remember that we divide this into components. Okay. Now, what about in the z direction? Well, the z direction and the y direction are essentially equivalent, so it's going to be basically the same. And here you have it. It's the same as in the y direction, but now we just replace uy prime by uz prime. And again, ux prime comes into the expression, even though into this expression, even though they're basically transverse directions. So so now we have the complete velocity transformations too. We have in the x direction, in the y direction, and the z direction, the transformation between velocities in these different reference frames.